Hi there, Mike here, and I'm going to cough very soon. Sorry. Start intro to hypothesis testing. We'll do several videos on this because there are many ways to do hypothesis testing. They all give you the same result, but you can do hypothesis testing via what we call p-values, test statistics, or looking at, say, the actual value of x bar. But let's just start from the very beginning. What's hypothesis testing? Well, point estimates give you a single guess. That's like x bar. Confidence intervals give you a region. That's x bar plus or minus, say, 1.96 s over root n. Alternatively, you may be wanting to ask a specific question about a population parameter. So we want to ask a question about mu. Does mu equal some value? And that's called a hypothesis test. So if we're asking a specific question about mu, that's a hypothesis test. Interval estimates, confidence intervals are really cool. We use them all the time, but occasionally we want to do a hypothesis test. We want to ask a very specific question about mu. This shows up a lot when we start doing modeling and we do regression. So hypothesis is a statement regarding a characteristic of the population. So population mean, population proportion, population correlation, not a sample statistic, but a population value. We normally talk about the mean or the population proportion, but there are many things we could do hypothesis testing on. Some examples: in 2008, 62% of American adults regularly volunteered their time for charity work. A researcher believes that this percentage is different today. According to a study published in March 2006, the mean length of a phone call on a cellular telephone was 3.25 minutes, and it probably cost like $10,000. A researcher thinks the mean length of a cell phone call has increased since then. Using an old manufacturing process, their standard deviation in the amount of wine put in a bottle was 0.23 ounces. Excuse me. With new equipment, the quality control manager believes standard deviation has decreased. These are all hypotheses about a population quantity. We test these types of statements using sample data because it's never possible or practical to see the population. There's always a chance of making a mistake. And if population data are available, there's no need for inferential statistics. If you knew the population, you would have everything. You wouldn't be talking about x bar, you'd be talking about mu. So recap, confidence intervals allow you to estimate a population value like the true mean or the true proportion and just put balance in our estimate. Give a confidence interval for the true average amount students spend weekly on alcohol. We might say, I don't know, it's somewhere between $20 and $60. So we don't know what mu is. We're pretty sure mu is in that interval. Hypothesis testing tests a specific claim about a population value. So is it true that the average amount students spend weekly on alcohol is $20? So here we're saying, is it true that mu equals 20? Now this is kind of interesting. We go back here, we don't know what mu is. We're pretty sure mu is in the interval 20 to 60. Here we're asking, does mu equal 20? If the answer is no, we don't know what mu is. We just know it's not 20. So in many ways you could say, well, why do I want to do this? Confidence intervals seem a lot more powerful, and I believe they are, but there are reasons you'll see where you want to test specific hypotheses. So parameter identification and hypothesis tests are carried out on all the Greek letters, mu and sigma and rho and stuff like that. In this section, though, we'll only talk about mu, and we'll come back to proportions in a couple more lectures. Hypothesis testing steps. Make a statement regarding the nature of the population, something about mu, collect data, analyze data to assess the plausibility of the statement. Now, there are two hypotheses involved here. There's what's called the null and the alternative. The null hypothesis, H sub O, is the statement to be tested. The null hypothesis is a statement of no change, no effect. It's assumed true until evidence indicates otherwise. It's from null, no effect, N-U-L-L, null. It's essentially the status quo. We want to see if we get a preponderance of evidence to reject the null and accept the alternative. The alternative hypothesis is denoted H sub A, sometimes denoted H sub 1 or H sub capital A, the alternative hypothesis. You're trying to find evidence to support it. We're hoping to reject the null and accept the alternative. The null is a statement about the population. And you don't get to see everything in the population. You get to see a sample. So it's very hard to prove a population statement. The null hypothesis might be all cats have 4 legs. You want to show that's true, you have to collect all the cats in the world, show they all have 4 legs. To disprove it, you have to show there's at least one cat that doesn't have 4 legs. My cat Casino has 3 legs. That would be an example of a counterexample of that statement. Now, there are different ways you can set up ho and ha. You can do what's called a two-tailed test or two-sided test. Parameter equals something, parameter does not equal something. Left-tailed or left-sided, parameter, the alternative is parameter is less than. Right-tailed or right-sided, the alternative is parameter is bigger than something. Notice that the null is always an equality here, and then the alternative changes. The null hypothesis statement of status quo where no difference always contains a statement of equality and equal sign. The null hypothesis is assumed to be true unless we see a preponderance of evidence against it. We seek evidence that supports the statement in the alternative hypothesis. So setting these things up are pretty straightforward. In 2008, 62% of American adults regularly volunteered their time for charity work. We believe this percentage is different today, so we would test the null hypothesis percentage is 0.62. And the alternative hypothesis, of course, would be, we just want to know if it's different, not equal to 0.62. Here, we want to know if the mean length of cell phone call is increased. It was 3.25. And now we do want to do a one-sided. Is it bigger than 3.25? It's a one-sided that way. We want to know here, we won't see how to do these, but it's straightforward once you understand the logic of hypothesis testing. Sigma is 0.23. We think new quality control measures have gotten better, so sigma is now less than 0.23. So that's one-sided to the left-tailed test, we would say. There are 4 outcomes when you do hypothesis testing. Reject the null when the alternative is true. That's a good thing. That's the correct decision. Do not reject the null when the null hypothesis is true. You've done the right thing. Reject the null when the null is true. Reject the null when the null is true. That's called a type 1 error. You've made an error. Do not reject the null when the alternative is true. That's also an error. It's called a type 2 error. So if, we look over here, if HO is true and you say it's true, you've done the right thing. If HO is false and you say it's false, you've done the right thing. Otherwise, there are 2 different errors you can make. And unfortunately, there's a yin-yang here. You try to maximize one, you minimize the other. You try to minimize one, you maximize the other. So which error is the more serious error that we focus on? Well, as an example, 62% of American adults regularly volunteer their time for charity work. A researcher believes the percentage is different today. So we're going to test P equal 0.62. And the alternative is that P does not equal 0.62. Type 1 error, reject the null when it's true. Reject the null when it's true. The percentage of people who volunteer is still 62%. We think it's changed. A type 2 error is fail to reject the null when it's false. Is that it has changed from 62%, but we think it is 62%. That's type 1 and type 2 error. According to, this is 3.25, and we're trying to test if it's bigger than 3.25. Type 1 error occurs, we reject the null when it's true. If the sample evidence leads the researcher to conclude that it's longer than 3.25 when it really is, type 2 says, we fail to reject the hypothesis the mean length of phone call in cellular telephone is 3.25 minutes, when in fact it's longer than 3.25 minutes. Now we have notation for this. Alpha is called the probability of a type 1 error. Beta is called the probability of a type 2 error. Which error is worse? We usually say that type 1 error is the worst one. Reject the null when it's true. You don't want to say the null is false unless there's a ton of information saying it's false. You don't want to reject the null that often. So usually we set alpha to be very small because we don't want to be having a type 1 error that often. As an example, this is a classic example. Defendant is not guilty is the null hypothesis. Defendant is guilty is the alternative hypothesis. And let's say this is a very small island where we're running a judicial system. And if you're not guilty, you're let go. And sadly, if you're found guilty, you're killed. So what's a type 1 error? Reject the null when it's true. So you're going to find a innocent person guilty. So in this harsh setup, you're going to kill an innocent. So type 1 error is you kill an innocent. Type 2 error would be let guilty, go free. So you're really guilty, but you find them not guilty. Which error is more important? In general, we'd say, well, the status quo is you're not guilty. We don't want to say you're guilty unless there's a ton of evidence to say you're guilty. So we don't want to have a type 1 error that often. As another example, the Master Tire Company has decided their new tire must last more than 45,000 miles or they won't market it. The null hypothesis is it lasts 45,000 miles. The alternative is that it lasts more than 45,000 miles. What's the type 1 error here? reject the null when it's true. Reject the null when it's true. So you're going to say the tire lasts more than 45,000 miles when it doesn't. The type 2 error says the tire does not last 45,000 miles when it does. So type 1 says you're going to say the tire is good when it's not. The type 2 error says you're going to say the tire is bad when it's good. Both of them have economic issues. Both of them have business implications here. So type 1 error says the tire's bad, we're going to market it. So you might have a lot of warranty work. There might be accidents involved with these bad tires on the road. You could have lawsuits against you, all sorts of bad stuff. You go out of business. Now, what's the type 2 error? You don't market a good tire. You're about to open up a plant in Alabama. You don't offer jobs to the community. Maybe you don't go out of business. All this R&D money you spend on research and design is wasted. They both have issues, but we would claim the type 1 is more serious. They're both called errors. So they're both errors and they're both bad, but you only get to choose which one to minimize. And most times, the alpha, the type 1 error, is the one we want to minimize. So we call alpha the probability of the type 1 error. It's the probability you reject the null when it's true. And we usually set it to be 5%. 5% of the time, we're going to mess up when we do hypothesis testing. 5% of the time, we're going to have a type 1 error. We're going to reject the null when it's true. Another caution, though, is in stating your conclusion when you do hypothesis testing. We can never accept the null hypothesis. Statement about the population, you never see the entire population. So we never say we accept the null hypothesis. We always say we either reject the null hypothesis and accept the alternative, or we fail to reject the null hypothesis. We never say we accept the null hypothesis. As an example, this is the cell phone time. Suppose the sample evidence indicates no hypothesis should be rejected, state the wording. Suppose the sample evidence indicates no hypothesis should not be rejected, state the wording. Suppose the null hypothesis should be rejected. We would say, since the null hypothesis is rejected, there's sufficient evidence to conclude the mean length of cell phone calls is now greater than 3.25 minutes. Now, this is where it gets tricky. If you fail to reject the null hypothesis, you'd say there's insufficient evidence to conclude that the mean length of a phone call is greater than 3.25 minutes. There's insufficient evidence to say the alternative is true. We can't say the null is true. We can't say all cats have 4 legs because we haven't seen all of them. We just can't conclude that the alternative is true. Yeah, it's goofy, but this is the way we have to say it. This is the logic of hypothesis testing. Almost there now. How do you actually do hypothesis testing? There's 3 different ways you can do it. They all give you the same result. Common interval method is the easiest classical method. Test statistic method's classical. P-value, really you run the computer to do that. Now, the confidence interval method is great if you have a 2-sided hypothesis you want to test. You create a 95 or a 1 minus alpha times 100% confidence interval, and then you just check to see if the hypothesis value is inside the interval or not inside the interval. Very straightforward, very easy to show with an example. You define your hypothesis, got to be 2-sided, construct a confidence interval, then you reject or fail to reject. We say accept. We shouldn't say that, but we reject or fail to reject based on whether or not the hypothesis value is in the confidence interval, yes or no. Let's show you an example here. Excuse me. So we have a big box of raisins, golden raisins, 15 ounces, and we want to see if the machine's filling the box of raisins correctly. So this says machine okay versus machine not okay. Mu of knots are a hypothesized value. Is 15 ounces being given in the box on average, or is it not 15 ounces? Machine okay versus machine not okay. And we have some sample data. We looked at 30 raisin boxes. We have a sample we have a standard deviation here. Well, we just run the R here, the 95% confidence interval. And if you're curious, tsum.test is a really nice package. It's in library BSDA, Basic Statistics and Data Analysis, BSDA. And I like it because you don't need the data. It just takes the summary statistics. So it's library BSDA. You may have to install the package. If you don't have BSDA installed, you can say install.packages BSDA once, in quotes, then load it in. Well, here's the confidence interval. We're 95% sure the true average amount of raisins in the package is between 4.95 and 15.2. We don't know exactly where, but it's somewhere in there. So mu is somewhere in this interval. Well, what can we conclude about this? We're asking, is mu equal to 15? Is 15 a plausible value for mu? Well, look at the interval. Is 15 plausible? The answer is yes. It's in the interval. So we would fail to reject null hypothesis. There's not enough evidence to say that 15 is not a plausible value. We would fail to reject the null hypothesis. And that's it. That's how you do testing of a two-sided hypothesis using a constable. What's the logic? Do we know the value of mu? No. We're pretty sure we know where it lies. We're pretty sure it lies in that confidence interval. So when we ask if mu equals 15, we just say, is 15 a plausible value? Is it in the interval? If it is, we fail to reject. If it's not in the interval, we would reject. What's the probability we make a mistake? Well, it's a 95% confidence interval. There's a 95% chance we're correct. So the probability we make a mistake is 1 minus that, 5%. That's called our level of significance, also referred to as the type 1 error. One more example of this. Manufacturer of sports equipment has developed a new synthetic fishing line. That company claims has a mean breaking rate of 8 kilograms. We want to see if that's the fact. We have 50, n equals 50. We want to test mu equal to 8 versus mu not equal to 8. We can only do two-sided intervals, two-sided hypothesis tests right now with this confidence interval approach. We have some sample data. We're going to check this out. The 95% confidence interval is given by this, and we're going to test mu equal 8 versus mu not equal to 8. What's our conclusion? Is 8 a plausible value? Look at the interval, it's not. We don't know what mu is, but there's strong evidence that mu is actually less than 8. What would we do? Reject or fail to reject? We would reject the null hypothesis and conclude that there's sufficient evidence to say that mu is not equal to 8. One more example, because this stuff is so straightforward. Robot welder, if it performs its task on average 1.325 minutes, it's an adjustment if it's performing its task in that amount of time. We want to see if it's performing that task in that amount of time or does it need adjustment. We want to test mu equals 1.325 versus mu not equal to 1.325. And again, no alternative, two-sided. Here we're doing a 95% confidence interval by hand. We've got a lot of data, so we're using 1.96 instead of a t. And what can we say? Is 1.325 inside there? Yes, it is. Fail to reject null hypothesis. The robot is not in need of adjustment. So again, if you have a two-sided test, something equal to it, something not equal to it, that's a two-sided test. Very straightforward, very easy to do via what we call a confidence interval. We'll show you how to do test statistic in the next video. Then we'll talk about p-values. So a lot more hypothesis testing stuff coming up. Thank you, and I hope you're having a great day.